So as I was mentioning today, we will be going over areas that are harder for people to learn from books. Just in general, I think people struggle more with the concepts that have more gray area. Like there's not a blueprint of something to do. Even hyperparameter tuning and things like that there are rules involved, and the rules you know what to test, you know what to check. So there's just a couple of different concepts that you run into that are just difficult to learn. So really going to hone in on those specific topics today. In order to get into full screen, I cannot see the chat on my other screen. So just FYI, so please unmute, give a question. Just please keep your questions to the class content itself versus something else. Just from last week, I actually can't post the video because it has to be so heavily edited because it went off book quite a bit. So remember to stay muted and remember to just ask questions about the class content itself. So again, these are the files that are shown at this link. But we're focusing on things that are harder to learn. So the first one is feature engineering. There are certain patterns that you're going to see in general that come up over and over again, but there's microphone not talking. So I'm actually going to stop. Please, if you get on and off, keep your microphone off. I don't have time to edit this recording. And it's very hard to keep my focus. If people are coming on and not muting themselves, it does it by default. Keep the default on. So we will be talking about feature engineering and bucketing and how to get your features ready to go into a machine learning model. We'll also be talking about incorporating business knowledge into modeling and how to get feedback from your stakeholders and actually pivot in order to do better modeling that fits better to their business needs. I'll also be talking about class imbalance. It's the thing on the daily basis that's actually hardest for even the most advanced data scientists to deal with. I have something actually that I have to do tomorrow that the model's just not working. I've tried pretty much anything I know how to do, and it's just a very difficult problem to overcome in some cases, and it's very common in the field. And I also want to talk a little bit about how infrastructure and design of code matters. It's not just your model, but it's how you set up the code that makes it reproducible. So going to be talking a little bit more about that. So I already covered that slide, so I'm going to jump right into feature engineering. So what is feature engineering? Feature engineering, just in general, you often have data coming in that's either not going to be useful for your model as is, or there's a testing component of machine learning where you try separate things. So a great example is shown on the screen here in the screenshot. And the data set that I've been using for most of my classes, there's a race variable. One of the first things you always want to do when you have a categorical variable is look to see how many groups or how many data points are in each group. So immediately when I plotted this variable or did a frequency table on this variable, I found that there were two groups, Hawaiian and Pacific Islander. Their Asian or Pacific Islander was one, and Native Hawaiian or other Pacific Islander was the other one. So they were less than like 0.2% of the data set, and they were split out individually. So when that kind of data goes into your model, it actually throws off the model a lot because there's not enough examples of those people to make good predictions with. This also comes down to model bias. So it's always something that you have to be cognizant of when you're creating models, especially when you're looking at people and outcomes. So race is a great example of that too. So say I deployed this model into production and I didn't have enough examples of certain types of people. And then the model in general wasn't as accurate for certain races versus others. That's not acceptable. So something that you always have to keep in mind is how to best group your data. So you can see here, I put Hawaiian and Pacific Islander in one group because it made sense and it made it a larger group and they were very similar groups to begin with. But in some cases you can't do that. So in those cases, you'll have to deal with your data, maybe do some upsampling, or say you were doing some image recognition model. You would have to go find more examples of people that are from different races, different genders, and make sure that that was sorry, I see that somebody can't hear, or I'm going to do a sound check. Can everyone hear me?
Yes.
Okay. All right. Thank you. So you always, both from a feature engineering perspective as well as a model bias perspective, you always need to keep an eye on these things. So just moving away from that, sometimes you just want to test multiple types of variables. So a great example is continuous variables and maybe bucketing those. I'll cover that a little bit more in the following slides. And then really, and as in every other part of machine learning, there's a test and check component of this. I always get the questions like, well, which one's better? Which one do I do? Well, the only way to know that is to try both and see how one might be better than the other. So this is feature engineering, and I'm going to go over the different types of feature engineering that you may do. So going into very specific areas. So the first one that I mentioned is the most common by far, is bucketing continuous features. So some continuous features are really granular, and that granularity actually creates noise, and that when you actually bucket it into distinct groups, often it's by quantiles, and maybe putting 10% of your data into 10 buckets, your data becomes better for the model because the bucketed variables have less noise and it gives more information to your model. Sometimes the continuous features are better because that continuum gives the model more information. I find usually continuous features are better than the bucketed version, but sometimes that's not the case. So you usually want to try both. An example of a way that you could bucket your features easily and actually put it into a pipeline so it changes in your deployed model. I put a link to a function here from the scikit-learn package, k-bins discretizer. That's like I don't even think that's a word. But this can help also, again, with what we talked about in the last slide with skewed distributions. So if we're bucketing things, even if you have continuous variables that are really skewed in one direction, that can also throw off your model. We see that a lot as well, especially where I work, which is in rewards and incentives programs. So for some of our clients, there's just really good customers that come back over and over and over and over again. So you have to account for those in your models. Sometimes you even have to split your population into two models. So you always have to be cognizant of what's your distribution. Are people throwing it off? Are there enough examples of everybody to get everybody right? So the other example we showed in the last slide is recoding categorical variables. A great example of one that I always try is if I have an age variable, I always try age and I try an age recoded variable and see which one is better. So that's another example, and that's a test and check. and then you would look at your model evaluation metrics and see which one was better with one versus the other. And another example is something that I haven't used a whole lot, but it's a really interesting way to look at different features. Actually, to take two columns or even more than two columns and concatenate them together with every combination of those features, and use two features or more features as one feature. And that's actually called feature crossing. So often this helps the model find interactions between your features. So if you have one feature that if, say, this feature's one, there is one effect on a second feature, but that impact or effect or impact changes if you have a zero group. Those are the times that feature crossing is going to be really effective in those cases. So it also helps your model learn faster. Is there a question? Okay, if there's no question, please mute. So now also this is actually one of those that that my direct reports have had a lot of trouble with. Please mute your microphones if you're not talking, please. Thank you. So handling missing values. Sorry, I have to mute whoever you are. This is very disruptive. So next time when you get on, please mute your microphones. So going back to what I was saying, so handling missing values versus not applicable values. So handling missing values, normally you would impute your variables. So if you have missing data, but sometimes missing doesn't really mean missing. So really, in actuality, sometimes missing values are really not applicable. So I'm trying to think of an example. I think I actually do on the next slide. So I'm going to jump to this. So an example that I've had is for one of our clients, we were looking at medicine and the number of visits that somebody had. Well, there are different products that are sold for this client, and we wanted to look at whether a person had received a product by their third visit. Well, they're really, you would have in general a binary 0, they didn't, 1, they did. But there's actually a third category. So when we would actually recode our variables, we had a lot of missing data. But in reality, it wasn't actually missing. It was those individuals who never even had a third visit. So in that particular case, we put that into a -1 bucket. And actually had a category for -1, being that they never had a third visit. It's not applicable, which is actually it's not as good as having a third visit and not using the product. And it's actually that's better. And then it's even better to have had a third visit and have had that product. So there's actually 3 categories, and not one of them looks missing, but it's not actually missing. So I've seen junior data scientists actually impute that data, which then leads to erroneous conclusions because it would be imputing something that wasn't really missing to start with. So that's an example of one that you really have to think about the business domain and understand what you're trying to measure in order to find the not applicable categories. Make sure you're bucketing them correctly. Are there any questions so far?
Just have a quick question.
Mm-hmm.
In terms of the feature crossing, if I'm going to have a model like GBM or a tree one, does that will automatically do this for me? Do I still need to do the crossing, creating a crossing feature?
So none of those models will actually do feature crossing for you. I think you may be thinking of one-hot encoding, and that may be what you're thinking of, but feature crossing is actually, you can think of it as concat in Excel, where it takes and pastes two columns together. So no models like naturally do that for you. So you would have to make that decision and do it yourself.
Oh, I see. I
Mhm.
mean, if the model will actually capture the interaction effect itself, like, do I still need to create the crossing feature?
So it may or may not. The model sometimes may capture that interaction, but it may not catch it as quickly, which means
Oh,
that your model might not train as well. So it may get there eventually, or it may, in some cases, not. If it's the model just doesn't pick it up, this actually explicitly tells the model to analyze it that way. And then that interaction comes up quicker. The model sometimes ends up better. And in some cases, it won't help because there's not a high interaction between variables. So
got
really, it's a guess and check there again.
got you. Yeah, that's really
Mhm.
helpful. Thank you.
Yeah, absolutely. So I wanted to give also an example of bucketing features and when you may use that. I've talked a little bit about like bucketing to get rid of noise, but there's also sometimes where bucketing also helps with those super users, like I was talking about. So when we bucket continuous features, we can also deal with that super users problem or extreme outliers with bucketing as well. So say we have that one group that's way out there. An example, I work for a rewards and incentives company, and we do a lot of promotions, but there are people who play the game, so to speak. So those individuals who play the game, they often use a lot more certificates than other individuals. So they're gaming the system, and actually using it as the rewards program as a way to get cheaper products. And they come in when they have a certificate versus when they don't have a certificate, they don't come in. That's something we see generally with a lot of our clients. But those super users are going to have a really long tail. So that may help your model if you're really trying to pick out those people, but it may also hurt your model and make it so that it's not predicting well for certain individuals. So sometimes when you bucket variables into like 10 groups, 6 groups, depending on what you want to do, that can help the model still knows that they're better customers, but they aren't so far away from everyone else. And again, this is so important. This is why business knowledge is so important. One, understanding when something's not applicable versus something that's actually missing, knowing when to bucket the features. So that's really important. Data scientists are not useful if they don't know the domain that they're working with. So that's one thing that I believe very strongly. And then the other one is actual data exploration and understanding what your data looks like. So this may not work as well if that super users group doesn't exist, but I'm not going to know that that group is there or not if I don't do some type of histogram or box plot or something to show that long tail so I can then actually account for it. So a model without exploratory data analysis before it is not a useful model. So you have to know the data, and often a lot of that comes from business knowledge and business domains. I work with an individual on my team for one of our biggest clients. She has been at the company for a very long time, and she knows the business backwards, forwards, and sideways. So often I'm newer to this, so I often go to her with a lot of questions. I say this more. that finding that person in the business who knows the data really well, or finding that person in for a client even that knows that data really well. You have to make sure you understand the data in order to model it properly. And I think this feature engineering conversation is a really great example of that. All right, are there any questions about the feature engineering side of things?
Yeah, I have a question. So, like you mentioned, so if we have a business people or a domain expert in the team to help you out, then this will be more helpful. How about the scenario when there is no one business people in the project or the team when we are working on? How do we extract the feature engineering on what basis?
So I've done this for a while, and I've never had a data set where there wasn't somebody who knew what was in it. Like, you have to be able to know what a feature is in order to model it properly. It's like junk in, junk out. I'm not convinced that you could properly do modeling without knowing what your data is. You can't just like put 50 features into a model as is and then press go and expect it to work without knowing what data to fill in, how to deal with those features. So it's probably not the most ideal answer, but I don't think data science can be done well without that at all. That's why I'm also not a fan of auto machine learning. I do think, at least at this point in the technology, it's still in its infancy and it doesn't do that human component. Knowing the data is important. The next thing I want to shift to is dealing with class imbalance. This is something I go up against all the time. No matter, for most customers, you see it at some point. It's just a very difficult problem to solve, and there's a couple of ways to go about it. And then this one is also really difficult to do because there's a lot of experience helps here. Because when you see certain patterns, you need to know to pivot or where to pivot and what to do. So this is generally one of the harder things to learn for data scientists. So I wanted to talk about it because I don't see this in books very often. And I've actually gotten asked about this exact example in interviews before, and actually in case studies for data scientist jobs. So it's clearly something that companies, for good reason, are interested in. So what is class imbalance? It's when we're trying to predict categories with an uneven distribution. Again, I like to always go with examples. So go back to the segmentation idea. For another client, we wanted to predict our best segment for a retail client. And the segment was called elites. Again, so we can try to predict early who those good customers are. The elites only made up 7% of the data. That's not a whole lot of examples of good customers to predict with. It was very tough to create this model and to make it accurate. So the reason that happens is the model places most of its emphasis on the bulk of the data, so 93% in this case, and there's not enough examples to balance out of those 7% of elites for the model to be able to pick them out. So often when you do this, and before you actually do any training of your model, you'll find that you have actually really, really high accuracy rates. Be very cognizant of this. This is why accuracy is not a good metric for evaluating models that have class imbalance. In general, it's good to know what it is, particularly because you're going to be asked by your stakeholder. But when you're evaluating models, accuracy is not a good metric to look at. So imagine we predicted, we had 99% accuracy, and we looked at why. So if I took every person in this data set and marked them as a 0, my model would be 93% accurate. And all I did was set the most frequent variable, most frequent class, and just set it to 1. My model did nothing, and it was 93% accurate because that group was not very common. And we still got every one of that 7% wrong. So that's also something to keep in mind here as well. So I wanted to talk a little bit more about this. So these models tend to be difficult to train just because we don't have those as many examples. I'm showing an example with a visual at the bottom right-hand corner of my screen of fraud versus no fraud. So if you took this, and there's not very many cases of fraud, most people don't do that by design. In this case, when we put it in our model as is, without any tuning, we're going to have a really, really high rate of false negatives because there's not enough positives to train with. So the example on the right is the example that you're going to see. How do we deal with that? There's a lot, thankfully, there's a multitude of different ways to deal with this in general. So I'm going to go over a couple of them. The first one, it's not the most ideal one, but it's often the one that works the best, just in general, is upsampling and downsampling. Really, this is very simple. We often take, if we have a really small group and a really big group, we will randomly choose a smaller group from our much bigger original data set for the most frequent class. And what this does is it makes it your classes equal in frequency in the number of data points that you have. The other option is to go with oversampling, where we take our smaller data set and actually randomly replicate them and make a bigger data set for our least common class. The reason this is somewhat problematic, and I'm going to go back to the question that we got in a previous slide, it goes to this too. The problem with undersampling is we're losing a lot of really valuable information about when we remove those zeros. And with oversampling, I just find that it doesn't usually work very well in practice. I always try it, but I've never actually used it in a production model. Undersampling tends to work better. I think just because it's seeing the same data points over and over and over again, it's not working very well. So that is an example of one way that you could go about it. I usually use this undersampling in only the most extreme of cases. I try everything else first to see if those work, and then if they don't, I usually try undersampling. And I try oversampling, but again, it's usually not as effective. So there's also ways to do the up and down sampling that get, oh, sorry, there's a question?
Yeah, do you have any like examples of like cases where undersampling was like really necessary? Like anything stand out?
Yeah, I can actually go back to this example. So the predicting the elite segment for the client that we did. So we did a segmentation, we turned the segmentation back, tried to predict who those high value segments would be early. So there's a couple other ways that I tried to deal with this problem first. We're going to go over a couple of them. Class weights is usually my first go-to. And in that particular case, class weights didn't work. No matter what I changed the weights to, the model still, usually it'll have a really, really high precision and then a really low recall, or vice versa. So tried that. I tried tuning my models in many, many different ways. If you're looking, because you'll see this problem with continuous data too, maybe change your loss function. None of that worked. I tried everything that I could, and then I went back and undersampled my data and made the groups more equal, and I got the model to be pretty good. It was in like, for a group that size, I think I had like an F score up at like 0.85, which is pretty good. For you generally see lower evaluation metrics when there's class imbalance. It's just the way it is. But for that problem, we got pretty close to that. So that's an example of when I had to do it. And it's because I tried quite literally everything else and nothing worked. Another example where you can do oversampling, but you actually don't use the same exact data points when you oversample. You vary those data points so the model doesn't see the same data points over and over again. That's called SMOTE. That's one way of doing it. There's also some other ways of doing it as well, but that's the most common that you'll see. So in this particular case, we find the minority class and we have that as an input vector. We then find its k nearest neighbors. So think back to prediction modeling, finding the k nearest neighbors. So if k is 3, I find the 3 nearest neighbors. And then we choose one of these neighbors and place a synthetic point between that neighbor and the particular value we're upsampling. So that it looks like a real data point, but it's not exactly like the data that already is there. And then you would repeat this data, these steps randomly with different data over and over again until your data set was pretty equal. I find that SMOTE doesn't usually work in a lot of cases. The reason is because often when you have class imbalance, your features are also imbalanced. So when you oversample, even when you do it this way, it's often not just your response variable that's the problem. It's often that your response variable and your features have class imbalance. And in those cases, SMOTE will not perform well. So in general, again, I've tried this. I've had limited positive results with it. I think there are a couple questions. I'm going to stop.
So the sample weight, correct me if I'm wrong, the sample weight which you told in the previous example of the classification will be more or less similar to this class imbalance way, right?
So this way, it's similar.
Okay. Thank you.
It's just that here you're resampling the exact same points and using the exact same points, sometimes even hundreds of times. So the model's seeing the same point 100 times. Whereas here, we're actually making adjustments or slight adjustments to the missing, to the ones that we're oversampling, so that the model's seeing similar points to what's there. They'll have similar relationships, but they're not exactly the same. That's the difference.
Thank you.
Any more questions? Great. So this is a very easy thing to test. Often also remember, you don't necessarily only have to use one of these things. In some cases, I've used 3 of these things all at the same time. So this is one that even when I don't have class imbalance, I always check this one. And just in general, because it's often super helpful even when you don't have much class imbalance. So when you do a classification model, the default is always if something's above 0.5, it's classified as a 1. And if something's below 0.5, it's classified as a 0. So why not try moving that threshold? So you could move the threshold so anything above 0.6 is a 1 and anything below 0.6 is a 0. So that's where ROC curves come in. You can, and that's shown here on this particular screen. The rock curves show the optimal threshold. So if you want to know a little bit more about rock curves, I believe it's in my 3rd class, and that'll be on my website. I can give that at the end of the class. But it plots the true positive rate and the true positive rate and the false positive rate. And then you can see as you change the class cutoff, your threshold and your evaluation metrics may get better or worse. So I wanted to find an example to show you. I'm actually wanted to show an interactive example. So I'm going to take this link and go in. So you can also use precision recall curves as well. That's going to depend on your use case. So here, let me see if I can zoom in so you can actually see what I'm showing. All right, so that should be a little bit better. So we have the true positive rate and the false positive rate at every threshold. So you see here, the threshold here is 0.43. We are looking at, in particular, the true positive rate and how that changes. So you can see as you change the threshold, the true positive rate changes. And once you get down to the threshold being 1, it's going to put everything in one category. You're often looking here where the curve is farthest out, or where it bows out the most. So right in and around here is going to be where your best threshold is. And you see that it's not 0. I'm sorry, it's not 0.5. It's a different threshold. This is just like a play example to show that. But you can also look at rock AUC curves, and that's shown here. And you can see how the false positive rate and the false negative rate changes as you change your threshold. So this is in my slides, so feel free to go and play around with that. But often just moving your threshold is helpful. And you see this bows out the most at this particular point, and that's actually our optimal threshold in this particular example. So this one is highly effective, I find, and it's very easy to implement. And my second favorite is class weights. This is done a little bit differently depending on what language you're using. Scikit-learn, which is probably the most common. This allows us to actually put into our model, there's a sample underscore weights parameter that you can put into most models. I believe gradient boosted trees, random forests have it. It allows you in your model training, you can say the class that has class imbalance, or you have a smaller number of examples of those, you can make them have a higher weight. So it's going to sound similar to what we talked about before, but this isn't a prediction model. So if I have less ones, I can set the sample the sample weight to be 1.2, and then if that it'll get basically give more weight or increase the value or increase the importance of something that has a higher weight. So if I set 1.2 for class 1, this will increase the value of a correct guess by 20%. And if I set 0.8 for the 0, it'll actually penalize them more, or penalize them, make it so that that is less valuable. So it's going to focus more on the higher weight. And if it gets the zeros wrong, it's not going to make as much difference in the model training. So it's penalizing it less. So if it gets the ones wrong, it's going to penalize it more because that class weight is higher. And often this is a way to get to the similar thing that upsampling and downsampling do, but you're doing it without getting rid of any information. So I usually try moving the classification thresholds, usually number 1. I try class weights, and then I usually try both of those at the same time. If neither of them work, I then go probably, depending on if I'm using big data or not, I usually try Smote. Smote is hard to implement with big data. So if I have big data set, I'll probably go down to downsampling and upsampling. And like I said, there's times where I've used downsampling, moving the classification threshold and class weights all in one model. So that's an example of something that you could help deal you with that class imbalance. So now I'm going to talk a little bit about infrastructure best practices. I've actually been getting into this more with my team. I've been kind of doing it for them for a while, but now I'm trying to start to explain the method to my madness, so to speak, and trying to explain how setting up your code, because this is more setting up your code, what are the best ways to do that? So modeling is useless without good data. I think you probably all already know that. So junk in, junk out. But it also matters how you set up your data. Because if you have a database that's not actually usable, you end up with a behemoth set of code that takes 2 days to run. I've seen that before, really. Like I've seen models that run 72 hours and that's because it's not set up correctly. It's not efficient. So one of those ways to make models more efficient is to actually set up your data correctly. My favorite way, and the way that I've been implementing and pushing in my own projects that I've been working on, are the bronze, silver, and gold architecture. So this is actually pulled from Databricks. I really like their terms because they're easy to understand. But often we have data coming in from many different sources, data lake, Kafka, and they're coming in as raw data. The bronze is raw data. You've done nothing to it. It's just sitting there. It's probably not usable in that state. The next layer is the silver. My motto is to only do ETL once. If you can do it once, you should never be repeating yourself when you're doing ETL, if at all possible. So this is often where SQL comes in and is really helpful. Getting those data, the data that, or the ETL that would happen across many different models. Because often for certain clients or for your business, you're going to be building multiple models off of one data set, multiple types of data off of that data. So you may have a time series model or maybe a customer prediction model. That data looks different at the end, but the guts are usually the same that feed into it. So getting that data into a usable state, anything that would be the same across models should go in your silver. Now the gold, you'll hear this sometimes mentioned, you'll hear the word feature store. Gold is where we actually have model specific ETL that happens. So aggregating your data to a customer level, or aggregating it for a time series model by day and customer. Depending on what you're trying to achieve, it's going to look different. But the input is only done once, and then we do the aggregation that is model specific, and that can go into AI models. You can go into dashboards. No matter what it goes into, the end product, this particular architecture in general has worked really well for me, and it helps you innovate quicker. Because if your data is ready to go, you have a feature store, all of your feature engineering is done, ready to go, you can pivot real quick. You can make models really fast, and you don't have to do any feature engineering. You may tweak it over time, but you're ready to go on day one to do any type of model. So this is something I think it's more on the data engineering side, but we data scientists also have to think about how our data is organized, whether we want to or not. It's still in our job description. So I wanted to share this as well. Right. So model pipelining is also something that I'm trying to push in general, and I always build my models like this. You don't want to create a monolith that used to be the way software was made a long time ago. And a monolith is where you have a really complex workflow, and you have everything in one script. So it's really better to split it out into separate scripts or separate chunks based on the function of that particular script or chunk. In order to do this, you often use model pipelining. So you may have an ETL script, a segmentation script, an offer engine script. This is something actually that I've done, final data formatting, and then it may go into a dashboard. And each one feeds into the other one. Why do you want to do this? It may seem more complex at first glance, but really it helps. It reduces the impact of errors. So say you had something go wrong in one script and certain points of data didn't feed into other parts of your pipeline. They weren't dependent on each other. Well, the rest of your pipeline will actually keep working. If one's not dependent on the other and they're split out, some of your pipeline will keep working in production. It won't break the end dashboard or model or whatever it is. So it'll be less likely to break down. It prevents duplication of work. So you can have the ETL layer go into multiple models. Whereas if it was in one script, you'd be doing a lot of copy and pasting, which is never good. It better enables collaboration. So often on data science teams, you'll be working on two models with the same data at the same time. Different, but you might have different people working on them. So it helps you be able to create two different solutions and then put them together if you design it correctly later. And it also simplifies debugging. So you'll know that if you get an error, you'll know if it's in the ETL script, or you'll know that it's in the final data formatting script. So it narrows down your search area for debugging and all of that of your code. So this, I've heard it called digital decoupling before. That's more on the software engineering side, but I think it's a good name for this. And it's really decoupling so that there's more independent streams, less likely to break down, and it's easier to fix or change over time. So finally, I always get a lot of questions about what's the cutoff? What is this metric, good or bad? And my answer is always like, I know this is not what you're looking for, but there's no cutoff. The metric that there is no good or bad metric. And a really great example is mean absolute error. Your mean absolute error is going to be dependent on how spread out your data is. There is no good or bad mean absolute error. There's only comparing one model to another model. So there's no cutoff or good or bad. We also often just just cutoffs in general, like when you're looking at correlation coefficients. What's the cutoff for a good correlation coefficient? Well, there's some rules of thumb there, but there's a lot of gray area. So you have to kind of live in the gray area, just in general. There are no right answers. And that's why data scientists are often people who like to explore data. They like to dig into it and understand the business problem and understand the data, because there really are no right answers in some cases. So that's why curiosity is really important and exploration is really important in this field. And the people who are that way are going to do better. But even though there's no right answer, sometimes you have certain keys to success. One, being domain knowledge. So you can narrow down the different, whether something's good or bad, by knowing the domain. Understanding the business goal. We talked about that as well. And understanding what each of the models do. Again, not a huge AutoML fan. I want to be able to go in and do a gradient boosted trees. You need to know what max depth is in order to pick a good frame. Like from 3 to 12, from 3 to 20, what range should I even look in? In order to know that, you have to know what the hyperparameter max depth means. And if accuracy or evaluation metrics go up when I change it, why did they go up? And that can lead you into more different areas where you have a better model. So understanding what you're actually doing with the model is very important. And I've seen a lot of mistakes when people don't understand what they're actually using because they don't use it correctly. And this is also why exhaustive model testing and validation is so important, because there's no right answer. So you have to test and check a lot of different things to find the best answer. So often that means checking evaluation metrics. Sometimes that means sharing your results with stakeholders midway through your project and making tweaks where needed. But exhaustive testing and evaluation is really important in all cases.